Okay, so now it's time to talk about non-uniform fields. And there's one type of non-uniform field, only one, that you have to master and have to be able to do something mathematical with. And that's called a radial electric field, or a radial field. Well, a radial field stems from a point charge, which kind of makes sense because radial, you can imagine, is kind of something spherical. So let's supposing we had a point positive charge. Now, by point charge, what we mean is one that's so small that we can basically consider it to be acting at a point, like a proton, is such a small object that effectively, as far as we're concerned, it's just a point. Well, the field lines basically, they just stem from that point out in all directions. Now, like with the uniform fields, if they ask you in an exam, make sure you spend some time and get your ruler out. Really, I could stop there. For equidistant lines, I'm going to put a few more in the gaps. But notice that I did the north, south, east and west first, because it just makes it easier to get them kind of evenly spaced. And then I can sort of put the ones in the gap. I'm not saying it's perfect, but that would be good enough for the mark. Almost. Because of course I have to put arrows on field lines. And of course this is 2 dimensions. In reality it's spreading out in 3 dimensions. Well, it's a point positive charge. So that means, doesn't it, that a small positive test charge would repel away. And that would be the direction of the arrows. So I'm going to put arrows pointing away from the field. And so that's how you draw it. Well, we could have a negative charge. What would the difference be? Well, hopefully you can kind of guess. It's going to look pretty much the same, except that, of course, a positive charge would now be attracted towards the point. So my arrows would be in the opposite direction. And look, I've only done the 4 lines there. It's a weaker field, doesn't matter, that's fair enough. And so that would be a point negative charge. Well, just to say one last thing, it turns out mathematically that if you had something like a charged metal sphere or ball coated in conducting paint which is charged or something spherical, well, the field that those create is actually very, very similar mathematically. I mean, it starts from the surface of the sphere, but acts in exactly the same way as if it was coming from a point charge. So, I mean, you can actually use the same methods of calculation, but just bearing in mind that there wouldn't be a field inside the sphere. So this is a charged metal sphere. So you can consider the field outside of the sphere from the surface and beyond to behave like a point charge again. So that's a charged positive sphere. So behaves like a point charge from outside of the sphere. Brilliant. Okay, so those are how you draw them. Well, of course, these are all on their own, but if you have them nearby each other, then they're going to interact. And that's the next thing that we need to have a look at. Well, the interaction of point charges or charged spheres, which you can consider to be point charges, are governed by this law, Coulomb's law. And basically this was found by experiment in the old days. Well, basically Coulomb's law is really interesting. It says the magnitude of the force between 2 point charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. So let's sort of put a bubble around there. Very important law. Make sure you're able to state that. So let's just see what actually it means. Well, let's suppose I have 2 point charges. Well, I'll call one Q1, and I'll put one over here, and I'll call that Q2. So, well, there they are. Now, they're obviously going to affect each other because, for example, if they're both positive, they're going to repel. If one's positive and one's negative, they're going to attract. If they're both negative, they're going to repel, etc. Well, first of all then, what Coulomb's law tells us is that the force between these is proportional to the product of the 2 charges. So it's proportional to Q1 times Q2. Well, that's the first thing. The second thing that we said is that it's inversely proportional to the square of the distance between them. So let's kind of, now if it was point charges, then, well, they're points. If it was spheres, it would be between their centres because they're behaving like point charges. So we're going to call that distance r. And if it's proportional to the square of the distance between them, then that means that f is inversely proportional to 1 over r squared. And then basically, these can both be shown by experiment, and then therefore we can combine those and say, well, that means that the force is proportional to Q1, Q2 over r squared. It's actually not that straightforward to prove that, but you can see why that sort of makes sense. So then we can write the equation again with a constant of proportionality. Well, this is quite interesting because we write this in two possible ways. We either write it with a constant k, the Coulomb constant, so we just say k q1 q2 over r squared. A slightly different way to write it, or the original way to write it, is to write the constant in a different way. So we write q1 q2 over 4 pi epsilon 0 r squared. Looks a bit crazy, that one. Well, it kind of originates because, remember, this is spherical. Well, 4 pi r squared is the surface area of a sphere, and you can imagine that, you know, a force is going to diminish in proportion actually to the surface area of the sphere. That's actually why it's proportional to r squared. But anyway, you know, we can easily swallow up 4 pi and epsilon 0 by just saying that k equals 1 over 4 pi epsilon 0. And so let's write that here, and write it in pink, and then we'll just explain what those constants are. So yeah, so in other words, k is 1 over 4 pi epsilon 0. Two different alternatives for writing the same thing. Well, they've both got names. Epsilon k is called the Coulomb constant and has a value of 8.99, so very nearly 9, often good enough to put 9, times 10 to the 9 newtons meters squared per Coulomb squared. And now you could, if you like, do 1 over 4 pi k to find epsilon naught and check that it works. I'm just going to tell you that epsilon 0 or epsilon naught is 8.85 times 10 to the minus 12. And well, I'm just going to for now put the units as they're usually expressed, which is farads per metre. You haven't met farads yet, but that's how it's expressed on the formula sheet. Soon enough you'll know what a farad is. Anyway, you just need to know the value for now. That epsilon naught, as I said, they've got names. Well, that is called the permittivity of free space. And this equation is only true in a vacuum, or something approximating a vacuum like air. So permittivity of free, which is what free space is, of course. And as I think I already mentioned, k can be called the Coulomb constant, more obviously. Brilliant, right, well, there's an equation. To use it, we'll just get straight into some questions. So following this, have a go, and if needed, follow up with the video solutions, and then we'll be ready to get really stuck in to radial electric fields.